So the talk here is about the moving goalposts of when you introduce Minkowski spacetime for special relativity. This is going to be my main reference which I'm using. Yeah, and it mentions some of the people before Einstein's special relativity 1905 paper that were dealing with similar ideas to Einstein. And then it goes on to say space and time are relative, i.e. they depend on the motion of the observer who measures them, and light is more fundamental than either. This is the basis of Einstein's theory of special relativity. Special refers to the restriction to uniform motion. And then it's arguable as to whether theory can be adapted to deal with acceleration, etc., but I'm going to pass on that issue. Then goes on to say Einstein did not quite finish the job, however. Contrary to popular belief, he did not draw the conclusion that space and time could be seen as components of a single four-dimensional space-time fabric. That insight came from Hermann Minkowski, who announced it in 1908 with the dramatic words, "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." Now, Einstein initially dismissed Minkowski's four-dimensional interpretation of his theory as superfluous learnedness. That's what Abraham Pass points out. And then, to his credit, however, he changed his mind quickly. The language of space-time, known technically as tensor mathematics, proved to be essential in deriving his theory of general relativity. So basically, Minkowski gave the four-dimensional space-time interpretation of Einstein's relativity in this interpretation, and then that was then used further on in general relativity, and that's really moving the goalposts. Einstein initially did not accept what Minkowski was saying, and then he changed his mind and he accepted it. It's moving goalposts from what special relativity was initially. As per Wikipedia, it says moving goalposts is an informal fallacy in which evidence presented in response to a specific claim is dismissed and some other greater evidence is demanded. That is, after an attempt has been made to score a goal, the goalposts are moved to exclude the attempt. The problem change to the rules of the game is that the meaning of the result is changed too. So Einstein, 1905, comes up with his theory, and it doesn't have Minkowski space-time with it initially, and then that gets added later, so that's moving the goalposts. So add Minkowski space-time to Einstein's 1905 paper on special relativity. That is an update, and hence moving the goalposts from what the theory was originally. It seems rather trivial change, just putting some math into a different form and interpretation. But what is done with it that then starts a major change, as Wikipedia notes. Change the rules of the game is that the meaning of the result is changed too. So adding Minkowski space-time to what Einstein's talking about in 1905 is changing things. Now this is a diagram of a Minkowski space-time, and time is represented here as going along the vertical line, and space is along the horizontal line. The x, particularly the x direction of space, is along the horizontal line, and from that sort of thing you can form these things called light cones. Now, Luhmann physics says not only are laws of physics simplest in inertial frames, but they should be the same in all inertial frames, since there is no preferred frame and no absolute motion. Einstein incorporated these ideas into his first postulate of special relativity. And what I'm pointing out in my videos, my other videos like this one, many of these sites dealing with relativity have got things wrong, picking up on just this issue of preferred frame and not the other issues in this particular video. Many of them say there is no preferred frame. The idea that there is no preferred frame comes from the relativity principle, the first assumption or postulate made in the 1905 paper on special relativity. Now, given there is a clock time dilation, then if person A, with the person B moving at a non-zero constant velocity relative to him, then he will say B's clock is slower. But given no preferred frame, then B will say A's clock is slower also, i.e. person A and person B will each say the other person's clock is slower. This sounds nonsense, as many who have criticised special relativity have pointed out. To see how relativists deal with this, then we need to look at the twin paradox. Now I'm going to use what this person says, Andrew Zimmerman Jones. And he says the problem is that in relativity only the relative motion is involved. So what if you consider things from this point of view? Then he stayed stationary the whole time, and it was Cliff who was moving away at rapid speeds. Shouldn't calculations performed this way mean that Cliff is the one who ages more slowly? Doesn't relativity imply that these situations are symmetrical? Now he's calling the twins Biff and Cliff. You're talking about still the same thing, twin A and twin B, or person A and person B, and he's talking about shouldn't it be symmetrical for these twins? He goes on to talk about these twins, Biff and Cliff. Now, if Biff and Cliff were on spaceships travelling at constant speeds in opposite directions, this argument would be perfectly true. The rules of special relativity, which govern constant speed inertial frames of reference, indicate that only the relative motion between the two is what matters. In fact, if you are moving at a constant speed, there's not even an experiment that you can perform within your frame of reference which would distinguish you from being at rest. Even if you looked outside the ship and compared yourself to some other constant frame of reference, you could only determine that one of you is moving, but not which one. He claims that twins are not symmetrical because one twin accelerates and the other doesn't. But let's look at how the twin paradox is dealt with by Minkowski diagrams. Now, this is a Minkowski diagram of the twin paradox. One twin is stationary and he's represented by the vertical line. He's not moving along the x direction. And the travelling twin is moving along the x direction, and he's moving first of all to the right, and then after a time he comes back and he's moving in the left direction. So he's moving along x to the right, then he's coming back moving in the opposite direction, and this is a turnaround. So eventually the travelling twin meets the stationary twin again at the top of this diagram. So you have a spaceship leaving Earth and turn around and coming back. You have the twin on the Earth, and you're ignoring that the Earth is moving and so forth. You're treating that as a stationary frame, and the other twin is moving off in the spaceship and he's turning around and coming back, and you're only considering that relative motion between the travelling twin and the stationary twin. Now the Minkowski diagram looks like this when you don't have turnaround. You can have just straight line motion without the line being bent, i.e. the yellow line. The yellow line is representing the light, so the other speeds will be at different angles to that. So this Minkowski diagram has brought in turnaround. You have a trip out, and then you have a return trip, and then you have, that's for the travelling twin, and for the stationary twin he's staying in the same position along the x-axis. He's not moving along the x-axis, and so he's just moving upwards in time. What we're talking about here, you'd probably have the travelling twin having to accelerate to begin with, and accelerate for the turnaround, but it's not being dealt with in this diagram as an approximation. We're just going to ignore things like that. We just treat it as the velocities. So this is the sort of diagram you get. You have two twins on the far left, an astronaut and his stay-at-home twin. They start off at the same age, and then the astronaut goes off on his journey, and he comes back on his journey, and he hasn't aged as much as the twin that has stayed at home. I dispute that sort of aging effect, but there is a difference between the clocks. The astronaut's clock has less time measured on it than the stay-at-home twin, and this is a clear case where it's not symmetric. The clock time dilation is not symmetric. The astronaut's clock is different to the stay-at-home twin. By relativity principle, it would be symmetric. Relativity principle is all inertial frames are totally equivalent for the performance of all physical experiments, and people take that to mean there is no preferred absolute frame. But with the Minkowski diagram, you have the preferred absolute frame coming in. The stationary twin is not in a symmetrical relationship with a travelling twin, and so it's a preferred frame situation. The stationary twin is in a preferred frame, and this is moving the goalposts. In the original 1905 paper, if dealing with no turnaround and keeping to constant velocity, which is constant speed and constant direction situation, then no change in velocity. There is no change in velocity, and then add Minkowski diagrams and allow turnaround, etc., have changed the situation from a no preferred absolute frame situation, have moved to a situation where there is one. With some relatives, it has left them stuck in a frame of mind where they say there's no preferred absolute frame, as per the 1905 situation, with them unaware that goalposts have moved to an updated situation or scenario with the Minkowski diagram has been introduced, i.e. Einstein's relativity just keeps changing things and moving its goalposts. Einstein's relativity starts off with relativity principle, then changes things. So some relativists like Tony Rothman says the term square brackets such as special relativity is probably the greatest misnomer in the history of science, i.e. special relativity is not really a relativity theory. It doesn't stick rigidly to the idea of relativity. What happens is 1905 paper or not by Einstein says there's a relativity principle, but then the Minkowski diagram idea gets added to it, and then you get this turnaround thing which you can do in the Minkowski diagram, and then that turnaround is introducing a preferred frame. You are suddenly not using the relativity principle anymore. You have moved your goalposts. Okay, thank you.